This is Technologically Speaking, the official podcast for the Department of Homeland Security Science and Technology Directorate, or S&T as we call it. Join us as we meet the science and technology experts on the front lines keeping America safe.
Hi, welcome to this episode of Technologically Speaking. I'm one of your hosts, Deepak, or D. Saini. Today, we have a very special guest to help us wrap our heads around an emerging area, which is quantum information science, also known as QIS. It's quickly becoming one of the most important fields of research in both the public and private sectors. Now, Dr. Ann Cox is our technical lead and subject matter expert in cybersecurity and quantum information science. Welcome, Dr. Cox.
Oh, thank you. Looking forward to the conversation today.
So quantum is such an emerging topic, and you're starting to hear about it more and more. Can you give us a little insight as to what might be the fascination around this topic?
So quantum information science is, people have actually worked in the area for, 30 to 50 years, but it kind of was not well known and like people who are like deeply academic, that kind of thing. Since 2012 to 15, there's been significant interest in quantum information science, and the last 2 or 3 years, things have just really exploded. It is going to be a disruptive technology. In my professional opinion, it will be as disruptive as cell phones or the internet. So it's on that level. There are various aspects of quantum information science. There's quantum sensing, quantum computing, and quantum networking. So people have worked on the theory for a long time, and they're now actually implementing that theory not only with laboratory trials, but in developing commercial products. Right now, when we think of I'll call it a conventional computer, or like your cell phone can do, like almost anything, right? With quantum computers, they're going to be more what I think of as special purpose devices. They're not general yet and may not be for many years, even decades from now. But for the particular problems that they are suited to solve, then you can get orders of magnitude speed up and in finding solutions.
So, of course, billions of dollars worldwide are going into quantum research, and it's already influencing products. Dr. Cox, to help people visualize what this looks like, can you talk through a little bit of everyday things we might use that already has a little bit of a quantum footprint in it?
Probably the device that is familiar to many people would be what they call a quantum television or quantum enabled television, QLED television. And they use what's called a quantum dot, which is a particular kind of qubit. And what that does, that quantum dot enhances both the color range and the vividness or the acuteness of the picture. When thinking about applications of quantum sensing in particular, the one that most people are probably familiar with is GPS, because I don't know about you, but I'm very dependent on my phone to find my way around, especially if I'm traveling. The atomic clocks on a GPS satellite are actually a quantum clock because it uses quantum phenomena. One that people are probably familiar with is an MRI, magnetic resonance imaging, where they put you down in a tube and do images of various parts of your body. I think there's actually a commercial product available currently where it's almost like a cap that you put on your head to do an MRI, and they are developing the technology for other parts of the body, like put a jacket on or something, so that you're not required to be down in this tube. For people who are of a certain size or are claustrophobic, the tube experience just doesn't work for them. And so
Yeah, I've been in that experience and I don't like it. So I'm so happy to hear this news.
And so also having like a cap you can put on your head would make it mobile. And so if you've got somebody in the emergency room that would need to have an MRI done, then it essentially can come to you like they do with X-ray machines now.
So Dr. Cox, what is S&T doing in the quantum information science space?
One of the concerns of both our current administration and the previous administration has been the encryption that we use throughout the government, throughout industry, and in particular here at DHS. So at DHS, my laptop, for example, has what's called full disk encryption. And so there are algorithms that are used to encrypt that information so that if I lose the laptop or if it's stolen or something, that an adversary can't get that information and use it against us. With quantum computers, we expect to have what's called a cryptographically capable quantum computer, meaning that quantum computer can break our current algorithms within the estimates are all over the place, from 5 or 10 years up to 20 to 30, maybe 50 years or longer. Because of the long length of time that we need to protect our information, which for government systems, DHS in particular, are anywhere from 25 to 50 or potentially even 75 years, there is a concern about what's called harvest now, decrypt later, meaning that our adversaries can collect the information that we normally exchange day to day here in DHS. They can collect that and then save it. And then when they get this cryptographically capable quantum computer, which many people think will be in the 10 to 20 year range, then they can decrypt that information, even our classified information. And so this is a significant concern. So there have been several presidential memos and directives to have us get ready to protect ourselves against this cryptographically capable quantum computer. So in order to do that, we need to know what's in our system. So we have a mandate to do an initial inventory within the next few months. Once we know what that inventory is as far as devices, we also need to know what algorithms are used for encryption and to protect the information on those devices. We need to be able to prioritize. Of course, it's going to cost a lot of money to move to new systems that protect against quantum computers. And so if you have a laptop that's going to be gone in 2 or 3 years, there's really no point in doing anything to it, because quantum computers are farther out than that. We're not going to have something that can break into your laptop within 3 years. However, if you've got a network element that you expect to be there for 20 to 30 years, then we need to figure out a way to protect that. Or if you have information in a database that needs to be protected for 25 to 50 years, we need to figure out the ways to do that. We're going to have to prioritize things as far as knowing what needs to be protected for what length of time. We need to know what algorithms are in use. Some algorithms can be updated, increasing the key size or doing other things to it and leaving it in place, where other things, the whole device will have to be replaced. And so figuring out those things is in some ways a monumental task, because pretty much everything we touch here at DHS is encrypted. And the other comment that I'll make about this is not the first time that we've needed to upgrade our encryption algorithms. Things have evolved over time, and every few years we need to make a transition. This one is a little more difficult because essentially everything has to be upgraded at the same time. And so it will be more costly and more labor intensive to get that done. But this is also not the last time we're going to have to upgrade our encryption algorithms. There's been some concern about why should we move to post-quantum encryption that will protect things, because we're just going to have to do it again. But really, that's been the whole process ever since we've had computers. Like as things evolve, we have to upgrade and do that.
What are some of the challenges and threats that QIS poses, and also some of the opportunities?
Well, the technology is what I would call special purpose. It's not going to solve every problem. I don't believe we're going to have a quantum computer in your cell phone anytime soon. On the other hand, for specific problems, a very famous problem in graph theory is called the traveling salesman problem. So if you have a salesman that has to go to, say, every capital in the continental United States, what's the most efficient way to do that? And then you have to define efficient. Is it the least time? Is it the least cost? Does this person have deliveries to make and orders to take? And so that kind of a multidimensional scheduling problem is one that quantum annealers in particular are very suited to solving. All right. There's a lot of natural phenomenon that is quantum in nature. And because of that, our conventional computers may not be as good as we would like them to be at actually working with those. A good example, if you take atomic structures for something like drug discovery, then it just doesn't take very many atoms until the computation that is required to figure out what those compounds are going to do and how to put them together in the best way and so on. It becomes computationally infeasible even for our supercomputers. The hope and expectation is that when we have quantum computers that are a little more capable than what we have now, that you can actually do those simulations and look at the different ways atoms are in a compound, or are they the same atoms but arranged differently? Because one arrangement might be a new miracle drug and another arrangement might be a poison or something very detrimental to the human body. And so there's a lot of hope and expectation that quantum simulation in particular will really benefit things like drug discovery, because right now it takes years and years to kind of sift through the potential candidates for a new drug, where with the quantum simulation, that time would be shortened by a significant amount and be able to find good candidates that, of course, would need a lot more research and development for, but it would shorten the time to at least find those initial good candidates.
What's the difference between a quantum computer and a conventional computer?
Quantum computing uses qubits instead of bits. Like in a conventional computer, you have a bit can be a 0 or a 1. In a quantum computer, a qubit essentially can be a point on a sphere, and so it can take on many values. And so even having just a few of them that work properly means that you can solve pretty difficult problems. So when we think of a quantum particle, sometimes it's things that we might be familiar with, like a tiny little piece of light called an optical qubit. And what makes something a qubit means that it can be in two different states at the same time. When we have a normal computer, we have bits, and those bits can take on the value of 0 or 1, but it's always one bit or the other. It's always either a 0 or a 1. It's never both at the same time. With a qubit, there are different kinds of qubits, and we're actually still figuring out what the best kind of qubit is to work with and build a quantum computer. There are actually thousands or millions of potential values for those qubits. And so instead of only being able to figure out one thing at a time, you can do a whole bunch of things at the same time. So you have something that's doing two different things at the same time, and that's called superposition, where it can be in more than one state at the same time. But right now, the scale's very small, and there's no what you would call quantum advantage. Like quantum computers don't do things better than conventional computers yet, but the promise is there. And within anywhere from 5 to 50 years, depending on who you talk to, it is very likely that we will have quantum computers that do show quantum advantage.
Why is a quantum sensor so much better?
Quantum sensing is better in certain situations because it's a lot more sensitive. When you think about the word quantum, it's really talking about the way the very tiniest things behave. So not just atoms, but subatomic particles. And when you get to that small, they just don't follow the same rules that we have. In a quantum world, things just don't work quite the same. And that it's both an advantage and a disadvantage. Quantum phenomena are very sensitive to environmental factors. And so because quantum is so sensitive to the environment, so when we talk about quantum computing, quantum sensing, quantum networks, it's really technology that's based on the tiny particles within an atom and how they behave. It's different than the things that we're normally working with. The very thing that makes qubits hard to work with, which is they're so sensitive to the environment. So you have cosmic rays, you have temperature, you have a lot of things that can interfere with a qubit. At the same time, that same property makes it a great sensor because it's more sensitive to the environment.
I have a question. How much math is involved in this work?
It depends on what aspect of the work you're talking about. It's a career opportunity because it's not just PhD physics or mathematics people that need to be involved. It's people all up and down the line. They need technicians, they need salespeople, you need advertising, you need all the things that you would have to run any kind of company. And so to be involved in quantum, you do not need a PhD in physics.
I'm also very fascinated by your background. Prior to your work at DHS, you spent 16 years at the National Security Agency, NSA, where you worked in the Office of Weapons and Space before returning to research. And also, I know with this work in quantum, NIST is looking for new math problems that are hard to solve for conventional and quantum computers. How do you feel your prior work before coming to DHS has led you to being at the forefront of this emerging tech?
So there's an organization called Women in Cybersecurity. It's pronounced WESIS. A professor from the University of Tennessee started that organization, probably 10 years ago, maybe a little more. And I was on a panel at their annual conference one year. And there were 4 or 5 of us on the panel. So I was from the government. We had an academic researcher. We had a woman who was in industry. We had somebody who was at a national lab. And every one of us did things in our career that we had never done before and never had any idea we were going to do when we started working. I think that is really the way of the future, that no matter where you start and what your background is, you need to be curious, you need to be enthusiastic, you need to love the opportunities that come your way and go for it. And being on the cutting edge of science and technology is really a pretty exciting place to be because it's going to be world changing. Life's an adventure, and this is part of it. And I'm not done yet. I've always loved learning new things, and this is a great area to be in.
Speaking of not being done yet, I'm so impressed by your education. You earned a bachelor's degree in mathematics from Brigham Young, a master's degree also in math from Idaho State, another master's in computer science from James Madison University, and you got your PhD in math from Auburn. Why stop there? Do you plan to continue?
Well, I guess my claim to fame that is that I actually did the PhD after I had 6 children.
Oh,
Um,
wow.
no, nobody knows what kind of things are going to happen to them in life. It turned
Yeah.
out that my husband had significant illness throughout our marriage. He passed away about 4 years ago, and so I needed to become the breadwinner. And my decision was that if I had to leave my children and go to work full time, which had not been my plan, I was very traditional and had planned on being a stay at home mom. But I said, okay, if I'm going to work, I'm going to have a career and have sufficient income that I can actually support the family. And so my husband and I kind of traded places where he was dad at home and had more of the nurturing and caring responsibilities for our children. And I ended up with this career, which I really didn't plan on, but it's been a good ride.
What message do you have for other women or just students in general that are maybe on the fence about STEM or going into any sort of related fields like you've been in? What kind of pearls of wisdom would you share?
So when I was working on my PhD, now they have like undergraduate experiences, research experiences, and so on. I did not have that opportunity. So the first time I had actually done any research was when I was working on my PhD dissertation. I actually was pretty scared. I didn't know if I could do it. And it turned out that the research itself was not as hard as getting it written up so that somebody else could understand what I was trying to explain. And so I would say, don't be afraid to try new things. Don't be afraid to get outside your comfort zone a little bit. And it can open a lot of opportunities for you, being willing to learn, being willing to do whatever the job requires. And I think that's the key to success.
That is such great advice, Dr. Cox, and I'm so glad you said that. I did want to ask one thing. Dr. Cox, when you were growing up, did you imagine that this would be what you would be doing with your career, or did you have something completely different in mind?
So when I was in high school, they gave us tests to see what a good career would be for us, and an interest test. And mine came out to be forest ranger. And
Oh, wow.
so yes, this is totally and completely different than what I anticipated. I took a math class every year all the way through high school. I was in a very rural area, and so they didn't have AP classes when I was in high school. They didn't exist. So, but when I got to college, then I still took a math class every semester and started as a double major in both math and music. I played clarinet for about 12 years and realized that to be a professional musician, I probably could have done it, but I would have had to practice about 6 hours a day. And I decided I did not want to do that. And so I kept up with the math and really didn't know what I was going to do with it. And I thought maybe I'd be a university professor. And then when the opportunity came to apply to work for the government, that worked out. And so it's been a good career.
Dr. Cox, is there anything I didn't ask or anything you want to add?
I would just like to encourage people to embrace the future. Even though there is the threat of our encryption not being valid, there's also all of this promise and all the new things that will come with this. And so just be enthusiastic and look at it as part of the way life goes and grow into it.
Dr. Cox, this has been such a great conversation. Not only have we learned a lot about a very tough and technical subject, quantum, to wrap our heads around, but we've also learned a lot of pearls of wisdom just about your personal journey and your career journey. And there's a lot there that we can take with us. So thank you for opening up to us. And we really appreciate this conversation.
Thank you for the opportunity to talk to you today, and I really appreciate the conversation.
This has been Technologically Speaking, the official podcast of the DHS Science and Technology Directorate. To learn more about S&T and find additional information about what you heard in this episode, visit us online at scitech.dhs.gov and follow us on social media at DHS SciTech. Thanks for listening.